My name is Benoit, and I'm CTO, co-founder of a company named Akineo. At Akineo, we are building tools to manage product information, to centralize product information. It's called the PIM, Product Information Management. It's like a CRM, but for product information. It's open source and it's PHP, but I will not talk at all about that today. I will talk about HTTP 3. And maybe your first reaction will be, HTTP 3, but HTTP 2 just came out. And that will be that kind of true, because when you look at the scale of the release of HTTP, HTTP 1.1 has been released 22 years ago, which is quite incredible, whereas HTTP 2 has been released in 2015, which is kind of yesterday in the scale of HTTP. And by the way, maybe quick question, who is still using HTTP 1.1 in their project? Don't be ashamed. Yeah. Yeah, maybe 1.0, but I won't ask this. You can be ashamed about this one, yeah. And so why is the reason why there's the kind of acceleration between the release of HTTP 2 and HTTP 3, which are kind of close together? By the way, HTTP 3 has not been released, has been announced last year. It may be released at the end of the year. We'll see that. But in fact, HTTP 3 is a normal evolution of HTTP 2. HTTP 3, in fact, is HTTP 2, but over quick. What the hell is quick? What the hell is quick? That's a good question. When you look at the network layers, the two topmost network layers are application and transport. The application has a meaning in terms of application. HTTP has verbs, it has a semantics, it means something for your application. The transport is just responsible to make sure that you can transfer data from point A to point B. But the transport doesn't care at all about the data. And the main transport we use today on the internet is TCP, the Transfer Control Protocol. For HTTP 3, in fact, we'll still use the same semantics, verbs, and features of HTTP 2, but over a different transport. Over transport named QUIC. So here we are replacing something that has been around for quite a long time, because TCP released in 83, last century, 1983. So around almost 40 years, by something else. So there must be some kind of problem with TCP here. So yeah, what's the problem with TCP? To better understand what's the problem with TCP, let's try to take a totally hypothetical situation. Let's say you walk into a bar. So when you walk into a bar, you will not go to the bartender and say, I want a beer. No, you won't do that. You will say, at least you will say hello. And if you know him or her a little bit more, like our friends Alice and Bob here in the picture, you will say, hey Bob, how are you? Hi Hal, I'm fine, and so on. And yeah, I'm pretty good, Bob. And that's the way you start the communication. It may seem pretty useless. In fact, as engineers, we may think it's pretty inefficient. We are wasting time doing that. But in fact, it's very important. It's very important for one thing, because it captures the attention of the person in front of you. You are sure that the person in front of you will be able to understand and maybe to respond to your request. So at this point, I'm sure that I created a reliable connection with the other person. So I can ask the main reason why I'm here. Can I get a beer? Yeah, and take a beer. If you look at how the network protocol works, before being able to execute HTTP request, I need to create a TCP connection. And TCP connection is a three-step process. You will start by the initiator of the connection, usually the browser, will start by asking for synchronization to the server. The server will answer with an acknowledgement of this synchronization, and the initiator, the browser, will answer with an acknowledgement of the acknowledgement. Then the connection has been established. It's a reliable and it's a good connection. You're sure your data will be transferred properly. At this point, you can do your HTTP request and get the response. In a more prosaic way, it looks like that. It's called the TCP handshake. And we find again this metaphor of saying hello to establish this connection. And the TCP handshake is a 3 steps that needs to be done in a certain order, but to do the next step, you have to finish the first one. So it means that all the latency will sum up during your different steps. Latency is a big word. In fact, when you look at network performances, because we will talk a lot about performances, there's two main words. They are latency and bandwidth. And to better understand the difference between latency and bandwidth, and maybe the relation between them, well, let's take another situation. Let's say that we have Alice on the bottom corner, on the right bottom corner, and Bob on the left top corner. Alice wants to send a message to Bob, but Alice got a problem, she lost her phone, and her internet connection doesn't work anymore. But Alice is smart, Alice is an engineer, so she's thinking about different ways to send a message. And the first system she's thinking about is using a sharp telegraph. A sharp telegraph is a device that has been created at the end of the 18th century, just after the French Revolution. There's three moving parts. There's on the both ends, there's kind of arms like that, and there's a middle part that can move as well. The way it works is that you build some shapes, and the people on the other side can see the shapes and interpret the shapes. So the way you transport the information is using light, because we are using the light that has been reflected on the device that goes through the eyes of the observer to get the information. You can build 92 symbols with this system, which is around 7 bits of information. And a good operator is able to do 3 symbols per minute because it's something quite physical to do. So we get a nice device, and so Alice is putting that on top of her house, and we know that we are separated by 10 kilometers from Bob's house. Now we know all the context, we can define the performances of our system. We have a very good latency at 3 microseconds, which is the time for the light to travel 10 kilometers, with a bandwidth which is not really great, at 0.4 bit per second. So as the bandwidth is not really great, Alice is thinking about something else. So she decides to buy a shipping container and fill it with SSD drive. And she finds the biggest SSD drive on the market, which is a 15 terabyte SSD drive. It's built by Samsung, it's a beast. And I did the maths, and you can put around 200,000 disks on these things. The limiting factor is the weight, because you reach 30 metric tons of disk drive if you do that. But the volume of data is quite interesting, because we have around 3 million of terabytes of data in this shipping container, which is nice. So she puts the truck on tracks. She put all the SSD drive inside the truck. And the truck has to go through 30 kilometers to go to Bob's house. Now we have all the parameters. The performances of this system, we have a very bad latency, because to get the first byte of data, we need to wait 40 minutes to have the truck that arrives at Bob's house. But we have a very nice bandwidth with 10 petabits, which is around 10,000 terabits per second. I don't know any network system that is able to provide this kind of bandwidth. By the way, this kind of way to transfer information is still used by big hosting systems like Google or Amazon to transfer data between data centers. So we now have the two systems, and we can compare them. So with the sharp telegraph, we have very bad bandwidth, but very good latency, whereas with the SSD truck, we have very good bandwidth and very bad latency. So the first thing we can see is that bandwidth and latency are not correlated, not always correlated. If we look at more systems that you may have used in the past or today, it's some evolution of mean to connect to the internet, dial-up modem, ADSL, optical fiber, bandwidth and latency for each of them. You can see that on the bandwidth side, we get 5,000 times better on around 25, 30 years. Whereas on the latency side, only 15 times better. Why? Because latency is a difficult problem. there's one physical limitation that provides us to easily have a better latency. And this physical limitation is the speed of light. Magnetic waves travel at the speed of light. Light travels at the speed of light. So we need to be able to optimize everything in order to optimize latency. We need to optimize the hardware as a device that connects the hardware, the applications, the protocol, and so on. And maybe you will tell me, should I care about latency? Maybe you shouldn't care. I mean, as web developers, should we care about latency? To answer this question, at the beginning of 2000, Jakob Nielsen defined the three main important limits in terms of user experience, which are, the first one is the 100 milliseconds, 0.1 second. Below this limit, the user has the feeling that what he's doing is instantaneous. It's a very satisfying feeling. You're clicking on a button, you get the result directly. Okay, it took maybe 100 milliseconds, but you have the feeling it's instantaneous. It's very good. After 1 second, the user flow of thought tends to go away. The brain is looking for something else. But we still keep the attention of the user. After 10 seconds, you lost your user. It was in 2000, maybe today it's more about 5 seconds. Because people are more, require more speed than before. So when we are talking about web performances, in fact, we are talking about web user experience. And the latency is maybe the enemy number one of web user experience. And we all felt that annoying moment when you are trying to work with a web application and it's slow. We all felt that. We know that it's very bad in terms of user experience. And it's quite funny because when you look at the history of HTTP, you can see that HTTP has been, for a long time, battling against latency. For example, in 1996, so 5 years after the first release of HTTP, which was HTTP 0.9, so HTTP 1.0 introduced TCP Keep Alive. TCP Keep Alive is about keeping alive, so your TCP connection. So you do a first connection to get the HTML page. Then you keep alive, you keep the connection open in order to do the other connection, to do the other HTTP request in order to get the other part of the page. So this way, you don't have to pay again the latency cost of TCP. In HTTP 1.1, this became enabled by default. So you had to put that inside your server and application in order to respect HTTP 1.1, and you have to enable it by default. In 2000, people started to use more parallel connection. When I mean people, I mean browsers. So we started by using 2 parallel connections on Firefox and Chrome, then it goes 6, 8 parallel connections. The idea behind parallel connections is you don't have to wait for the first connection, so for the first request to get the response, so you can do more things in parallel, so you reduce the latency. At the beginning of 2000, between 2010, people realized that there was very nice features in HTTP that was local cache, maybe being able to get very good performances, very good latency performances by using local cache instead of asking if there was, if the resource has been modified. Because if you ask if the resource has been modified, then you pay the latency. So instead of using HTTP 304, which is the resource has not been modified, we use local cache. And in 2015, HTTP2 streams have been, HTTP2 has been released with 2 main things, the streams. The idea of the stream is to use one TCP connection and to multiplex the HTTP request and the HTTP response is the same TCP connection, always in order to avoid this latency of the TCP handshake. And even better, HTTP2 push is about doing one request. And as the server knows that I will certainly ask for the other resources, the server is pushing me the HTML page and some other part of the HTML page, like the JavaScript or CSS elements. So you see that HTTP has done a lot to try to reduce latency. But in the past 10 to 5 years, we made the latency worse. We made the latency worse because we want security. And to do security, we need to, on top of TCP, we need to encrypt our connection, to encrypt our data. So we use TLS, and TLS is a protocol that uses 5 steps uncheck. So it means that today, when you're using HTTP2 or HTTP 1.1 with TCP and TLS, and you should use TLS, obviously, it looks like that. You have to do 8 steps before even being able to do your HTTP request. So that's where QUIC and HTTP3 will try to do something. Because when you look at what this means in terms of latency, for example, in 4G, I get almost 1 second of latency before being able to do HTTP, and it's even worse in 3G, as you can see here, with 2 seconds. One of the main problems is that TCP doesn't know about TLS. TCP is a very nice abstraction layer that makes sure the data has been sent from point A to point B, but doesn't know that the data must be secured. So we had to use TLS on top of it. And TLS doesn't know about HTTP as well. So we have abstraction layers on top of abstraction layers, which create this bigger latency. So the idea is to replace TCP and TLS by something else, which is QUIC. QUIC now just means quick, but when it has been released, it was Quick UDP Internet Connection. And remember UDP here, we will talk about that later. And the quick uncheck is a 3 steps uncheck, pretty similar to the TCP uncheck, except this includes encryption. So in the same protocol, you get encryption and transport with only 3 uncheck instead of 8 as we saw before. This means that in theory, you get almost half the latency of using, compared to using TCP and TLS by using QUIC. But you may say, okay, it's based on UDP. And you may have heard that UDP is unreliable. And that may be the reason why TCP has been created. And TCP is the main protocol used on the internet. So maybe the question is why internet has been created? Anybody knows why internet has been created? Communications, but who has created? Military. Yeah. At first it was called ARPANET. ARPANET, it was a project of the Department of Defense of the United States, with the main idea is to have a very reliable way to transmit information, even in a case of a catastrophic event. So we are in the 80s, at the end of the last century. What kind of catastrophic event people were fearing at this time? Nuclear war. So the internet has been kind of created to fight, to be able to continue to transmit information even in case of a nuclear war. So the internet is kind of child of the nuclear bomb. And the web is based on the internet. We are all web developers here, so we are here thanks to the nuclear bomb. Let's think about that a little bit. But okay, so how TCP works exactly? Let's look at this situation. I want to send from my laptop a message to one server here. My important message is first cut it into small pieces, which are called packets. And the packets are sent to the internet, which is an interconnection of network. So the first packet goes through this path because the routing protocol, this routing algorithm decided to send this way. It goes this way. At some point, the routing algorithm found out there was a shorter path to go to the destination. So the second packet goes through this path. The third packet follows the second packet. The second packet arrives before the first packet. We got a catastrophic failure. No, not a nuclear attack, but more like a device just got destroyed or some problem on the network. So the second packet arrives, the first packet arrives. The fourth packet, thanks to the routing algorithm, find a way around the problem. So it goes around the problem. TCP is able to detect that the packet has been lost, so a packet is re-emitted. The third packet is re-emitted, follows the packet fourth. They all arrive at destination. TCP is able to put back the packet in the right order because they just get all in the wrong order, and to decrypt my message. This is cool. This is pretty cool. That's what TCP does. The same situation with UDP will get to this point. I will lose the third packet forever. The packet will be in the wrong order. There will be no way at all to find out what was the message. So it means if QUIC wants to replace TCP, it means that it has to take care of all the packets, to take care of remitting the packet when they get lost. And it will have to do that at the browser and server level. So we are kind of reinventing TCP on top of UDP. But this has some interesting effects and wanted effects, obviously. So finally, Alice found her phone. It was at Bob's house because she found another solution. She just walked to Bob's house to send the message. So now she's going back to her home. She has her phone. Her phone is connected to the cell tower through 4G, for example. And she wants to access a server which is obviously on the cloud. Thank you for the one. Thank you. And so the browser makes a TCP connection to access the server through the network, through the cell network. So I got a nice TCP connection. Then Alice is walking toward the house, and at some point, in the house, the Wi-Fi now works, and the smartphone catches the Wi-Fi. What happens in this situation is that I lose my TCP connection. And Alice get this nice error message. I don't know if you already get this message. Yeah, because I get it every morning. Because to open my office door, I have to use my Google account. So we have a small web application where you put your Google identifier and credentials. And when I'm walking to my office, I'm using my 4G connection. I open the application. And at some point, my phone catches the Wi-Fi of the office, and I get this error message every single morning. So Alice is in the same situation. So what happened in this case? The browser restarts everything from scratch. It has to restart the whole TCP connection and the whole HTTP request and maybe a response that has been done. So I start a new TCP connection from scratch. Then I can get my answer. The problem is TCP is strongly coupled to the network connection. And we know as web developers that, as software engineers, that strongly coupling things together is a bad thing because it means that if the connection dies, I lose my TCP connection if my network connection dies. In case of QUIC, what will happen is that same thing. I'm connected to the cell tower. I want to access to the server. I open a QUIC connection. And the nice thing about the QUIC connection is that it's from the operating system point of view, there are just UDP packets, independent UDP packets. And all the magic stuff are done on the browser and server side. It means that when the smartphone will catch the Wi-Fi connection, the QUIC connection will continue to remit packet through a new network connection, but without losing the QUIC connection, which is managed at a higher level. And in this case, I get the result I was looking for, without losing my HTTP request. So yeah, QUIC is loosely coupled to the network connection, which is a pretty good thing in terms of usability. Another problem with TCP, maybe you heard about this one, is head-of-line blocking. End-of-line blocking is even more strong in HTTP2 streams. So the idea of HTTP2 streams is that you multiplex multiple requests in the same TCP connection, sorry, and then the HTTP server identifies which resources belongs to each request and send them back multiplexed to the browser. They are sent back into TCP packets. You are in TCP connection. So I have 6 TCP packets. I send them to the network. At some point, I lose the first one. The others continue their journey to my browser. The first one is remitted, but several seconds later, because to remit a packet, there's kind of timeout system. So several seconds later, we know that it didn't arrive, so we need to remit it. The packets arrived, and at this point, the browser doesn't have anything, cannot do anything, because at this point, the operating system cannot provide any information about the packet because to read the packet, it needs to get the first one. It needs to get the one that are in the head of the packet. So the browser has to wait for the first packet to be remitted to be able to display the different resources. When you are using a quick connection, so yeah, it's a interesting point here is HTTP to stream, in fact, can be worse than using HTTP 1.1 parallel connection when you have bad connectivity. HTTP to stream is like putting all your eggs in a basket, and if you remove one egg, the other are slow. Make sense? No. So HTTP to stream will be better thanks to Quick. We'll see how. Because, OK, I do my multiplexed request. I get my payloads. This time, we create UDP packets, which are independent from each other. They get sent to the browser. Same scenario here, I lose the first one. But the other one arrive at destination. At this point, they arrive at the browser level. And the browser level just say, OK, it seems that I have 3 streams. One of them is missing one packet, but the other, I can use them. And at this point, you are able to display the resources to the user. So from the user's point of view, it doesn't have to wait for this small packet that has been lost to display the other resources. After the delay, of course, I can display the first resource, but I already had a far better user experience by using Quick with HTTP2 streams. Because thanks to Quick, the different HTTP streams are now independent from each other. There's no more head-of-line blocking. As a web developer, what you need for me in terms of HTTP3, just a reminder, HTTP3 is HTTP2 on top of Quick. So it means that all the semantics, all the new features of HTTP2 will be kept the same. So HTTP3 is mostly a drop-in replacement for HTTP2. So if you start working on HTTP2, you will benefit from HTTP3 when it will be out. That will be my advice. Of course, HTTP3 is not going to be there tomorrow. There are some challenges. The first one is the support. Today, there are 3 servers supporting HTTP3, very high speed, which is proprietary. Caddy, which is kind of used now more and more used on the container-based system. And H2O that has been done by Fastly. I don't know if you know the CDN system Fastly. They open source their server. On the browser side, Chromium on Chrome as Quick support, Opera 16 as well. And for now, on the side of Firefox, Quick is just a ticket on their ticket system. They didn't begin to work on it right now. Another problem is firewall configuration, because most of the time your firewall configuration to access your HTTP server will be about opening a TCP connection to 80 and 443. We will have to change that to be able to use a UDP. That's the reason why there's a workaround that has been implemented in Chromium, which is about opening 2 connections at the same time, one Quick and one TCP, in order for the first one, if the first one that gets a good answer win, and the other one is discarded. Another problem is that on some routers, UDP is slowed down because of quality of service issues. UDP is used a lot by malwares and by some peer-to-peer sharing things. So some router by default makes the UDP packet pretty slow. So that's another problem that needs to be solved. In terms of maturity, I said that HTTP3 has not been released, but Quick has been launched 6 years ago, in fact, by Google. It has been enabled in Chromium since 6 years ago. See, if you're using Chromium and if you're using some Google services, you're already a guinea pig of Google on Quick. You're already using Quick for some years. Since a couple of years as well, Chrome itself has Quick enabled for Google web servers. And now there's an ongoing standardization by the IETF, which is draft number 20, if you want to go there. You can see on the draft that the changelog is getting more and more stable because there's less and less changes on the draft. So we expect at some point a stabilization of the specification. And the first interconnection has been done at the end of last year, which is not so long ago. In terms of open source, there's some interesting projects. The first one is the KDE implementation of Quick. Dev sisters are people that extracted the Chromium, the Quick client Chromium side and put them in an independent repository. So if you're doing C++, you can use it. There are an implementation example of the Quick server on the chromium.org website, and that's the Fastly implementation. The CDN is quite interesting because when you think about CDN, latency, it's their business. That's the idea of a CDN, is to reduce the latency. So they jump on the bandwagon of Quick already since last year. And you can see that it gave some nice performance improvement on the Google CDN side when they switch on Quick on the beginning of last year. In terms of reverse proxy support, maybe some of you are using Varnish. Yeah, oh, yeah. Okay, so Varnish may be one of the most used reverse proxy in terms of performances with Nginx. And at the beginning of the year, they decided that will be their main focus for 2019 to implement Quick inside Varnish. At least this will remove one big aspect of Varnish that was the support of TLS, because Quick includes TLS, so you won't have to have a TLS proxy on top of Varnish anymore once they implement Quick. Another problem with UDP is CPU usage. Today, UDP is 3 times more CPU intensive than TCP. And the reason is it's kind of obvious when you know that it has been 30 years of optimization of TCP since the release of TCP in the 80s, or around 40 years almost. A lot of things have been done because TCP is the most used protocol on the internet. So a lot of things have been done to optimize TCP that has not been done on UDP. So a new project is starting on the Linux kernel in order to implement the same kind of optimization features that has been done from TCP, but this time for UDP. Okay, so to finish, some takeaways for this presentation. First thing, yeah, the Quick latency is far better than TCP and TLS. That's the main point of using Quick and HTTP3. HTTP3 really allows HTTP2 to meet its full potential. We could say that HTTP3 should have been HTTP2, in fact, because as we saw in some situations with HTTP2 streams, using TCP makes it worse than using HTTP 1.1. And another interesting thing is that, as I said, you can start implementing HTTP2 and you will benefit from HTTP3. That's the main idea. We don't know when it will be released, but at the same time, we know that it has already battle tested since 6 years, by Google. And there's still a lot of work to make it happen, obviously. So thanks a lot. There's some, if you want more information, this one is about Daniel Stenberg, the author behind curl. He's doing a lot of things on Quick and is part of the Quick working group. And there's some good definition on Quick on the chromium.org website. And don't hesitate to give me some feedback about this presentation. Thank you very much. I think we have time for... Yeah, for question, yeah? Yeah.
Is Quick faster than just doing straight 1.1 on port 80 without any TLS and let's say multiple connections?
The question is if we don't use TLS, is there the point of using Quick? Mm-hmm. Okay. I think at least for the if you are inside one network talking with communication between two applications, and the security is managed outside of these things. No, it's not. There's not a lot of things interesting in Quick, but the main idea of Quick is really about bad connectivity, so a lot around the smartphone thing. The fact that you can switch network is as well something that will be helpful when you're using a smartphone. Yes?
So as I understand it, with normal TLS, there's a
work the same way as TLS? Is it just TLS baked in a layer down, or does it work
Yeah.
differently?
Yeah, so the question is, does Quick uses the same mechanism as TLS, yeah, to do the encryption part? And the answer is yes. In fact, it's using TLS directly. It's shortening some part of the handshake, which are not really needed, so it helps on that. But inside it is exactly the same. We are using the same certificate, same asymmetric encryption. Yes?
You said that quick is 3x. Well, the quick is 3x time much than TCP, but is it just route TCP connection or TCP with TLS over it?
You mean in here? That's what you. Yeah. Okay. So the question is, Quick is Quick. In this case, we are using more TCP. Anyway, the question is, as Quick is using via UDP 3 times more CPU usage than TCP, that means that TCP and TLS is using far less CPU. Here it's really about TCP and UDP in this situation. So it doesn't take into account all the encryption part that is done by TLS. It doesn't take into account the encryption part done by Quick as well. It's really on the layer of transport, on the transport layer, which is really about UDP and TCP here.
But it's not really fair because TCP handshake is most time consuming operation.
Yes, but the idea is when you look at the CPU taken by the kernel to transfer information, because TLS is not done by the kernel. It's done by the web browser and the web servers. But if you only look at the CPU used by your Linux kernel, if you use TCP, it takes 3 times less CPU than using UDP. That's the idea. Any other question? Yeah. Excuse me. Ah, that's a good question. How the packet loss is solved? In fact, if we go back here, that was yes here. The problem of the packet loss. We don't solve it. In fact, the problem is not really solved. We still have to re-emit the packet if the packet is lost. But what is better with Quick and HTTP2 streams is that you can consume the packet that already arrived at the browser level. You don't have to wait for the first packet to come to be able to use the data that are in the other packets. That's the main idea. But the way the packet is re-emitted by Quick over UDP and TCP is really similar. Really, really similar. It's ARQ, it's automatic request. It's a way to automatically send packets in case of problems. So it's implemented the same way. Yeah. But that's a good question because there's another way to manage lost packets is to use forward error correction, which is a way to send more information, so to use a little bit more bandwidth, in order to say that, to kind of recover from packet lost without re-emitting packets. And one of the good things of Quick is that now it's implemented on the application level. It will be far easier to implement new features in the protocol than a protocol implemented on the kernel level, because you don't update your kernel every day. You may update your browser every day. So it will be easier and more flexible in order to add new features in the future.
So in UDP, right, the packets are going to arrive in the wrong order very often, right? And so in TCP, this was corrected at the operating system level, right?
Yeah.
But now it's going to be up to the application to put the packets in the correct order, right?
Yes.
And would that result in added CPU usage, or is it just we're transferring some processing away from the kernel, and now it's the application that's going to do it, so it's pretty much going to be a wash?
Yeah. The question is, now that the reordering of the packet is done at the application level instead of doing it at the kernel level, does it use more CPU? good question, because theoretically speaking, it will use the same level of CPU in the application level or in the kernel level. But in fact, the kernel, when you're using, there's not many kernels. You know, you have the Linux kernel, you have the macOS kernel, the Windows kernel. So when there's an optimization effort that is done, it's done on one thing. But if there's a lot of different ways to implement Quick, a lot of different applications, they may not benefit from the same level of optimization because the level of optimization will be diluted over different implementation.
Sorry, I kind of have a related question because right now the nice thing about HTTP and TCP right now is that the client can be dumb, right?
Yes.
So, you know, I can have wget, I can even telnet a request to port 80, right? I know that what I get back is going to come back in order, right?
Yeah.
But now, like all those command line clients are going to have to, if they're going to speak quick, they're going to have to be able to reorder the packets correctly, right? Otherwise.
Yeah, that's a good remark. The remark is now that we are transferring a lot of logic inside the application instead of being on the OS side, it means that the HTTP client will get more and more complex. And they will say, yes, and it was even true with HTTP2. In fact, the easiest, simplest, the most simple HTTP client was Telnet before HTTP2. Because it was a human readable and human writable protocol. With HTTP2, it became a binary protocol. So yeah, there's a trend of putting more and more logic and more sophistication and complexity inside the application. Is it a good trend? I think there's always a trade-off. It gives you more power, more features, more flexibility, but more bugs, maybe less optimization. I think a lot of things are like that in software. Yeah, kind of. I know that on the question is, does libquick is helping on that point? Yeah? Yeah, okay. It will help, but if you're using something like curl is re-implementing, they are re-implementing themselves quick on their side. So, because I don't think curl is written in C++, and Chromium is written in C++. It's not directly usable this way. And there was another question behind it.
Yeah, it's just about the confusion about if you use a curl utility or wget, they also need to implement the same correction of packages and stuff. So there will be a lot of libraries for different languages implementing the same stuff.
Yes, it's a remark similar to what Chris said. It's a lot of complexity will be added to all the tools that need to speak HTTP.
Because it's now on a higher level.
Yeah. Yes. That's a good question. The question is, will there be a kind of net neutrality problem as Google has been the creator of Quick, is the provider of the main use browser, which is Chrome? Yes, that's a good question. It's a question of the standard. When you have already an implementation that is being used by a lot of people, is the standard really totally neutral? Or is it influenced a lot by who did it at first? I would say it's influenced a lot, and I'm not sure it's always a good thing. Yes, Larry?
So it sounds like Quick is essentially TLS over UDP. Are there intentions to use Quick for things other than HTTP?
No, okay, the question is, does Quick is there an intention to use Quick other than with HTTP? And in fact, that's already the case. If you're using Google Duo, which is a FaceTime of Google, it's already using Quick behind the door. So I think Google will use more and more Quick for their application, even the ones that are not using HTTP. And yourself, if you have the Quick libraries, you can build your own application on top of it as well.
So it was designed to be...
independent of HTTP. There's the idea of matching the HTTP2 streams inside Quick streams, but it's an optional feature, so you don't have to implement it. Yes?
You said that the fallback strategy was basically to kick open an extra TCP connection.
Yes.
Right? Is that the same fallback strategy that was also being, or is also being used for IPv6 and IPv4 connections? Like kicking open two connections and then killing the one that doesn't respond?
Yes.
Same type of.
The question is, as there's a kind of fallback on the TCP connection on Chromium, if there's no way to reach through UDP, the server, it's the same as IPv4 and IPv6. Yes, it's the same things. Very similar way of working. You use twice the resources, but at least one of them will reach the destination. Okay, thank you very much. Thank you very much.